a computer architect. I work in a division called as Processor Architecture Labs. That's part of Intel Labs. So Intel Labs is basically the research division of Intel, right? And I'm located in India, in Bangalore, Intel Bangalore, right? So we look at next generation processors, what should be the architecture for that, how can we improve the power performance of next generation Intel's cores, right? So what I'm going to talk about today is about single thread performance. So how many of you have done a basic course in computer architecture? Okay, good, nice. Right, so can somebody define what is single thread performance? I'm supposed to give chocolates, right? If you get the answers right. So that's a dairy milk, right? Who can define single thread performance? To some extent, it's correct. I'm just going to throw this. Oh, missed it. Okay, so single thread performance is when you write a program, right? It's mostly single thread when you write, right? So you start from something, you end at something. Now what you can do is you can take the program, and if the program does some parallel stuff, you can split it into multiple threads that can potentially run on parallel cores, and then you can combine the results together, right? That becomes multi-threaded. But single thread is typically the way we write programs. So if you've written a program, you would have mostly written a single thread program, unless you did something special to make it multi-threaded, right? So single thread is like the core in terms of performance, right? When you improve the performance of one thread, you end up improving the performance of every thread, right? So we're going to talk about how single thread performance has improved over the past so many years, right? What have we done as computer architects to improve performance of the processors, and what are the challenges going forward, right? And I've been asked to motivate you guys towards doing a research, and single thread performance is probably one of the toughest things to improve, right? So we need like bright minds looking at it, and I think someone from here is probably going to bring in the next leap, right, in single thread performance, right? So it already concluded with that. So okay, how do I go back? The left button. Which one? This one? Okay. That's fine. Yeah. Okay. We'll go back to the computer, right? Okay, so let's get started. Okay, so microprocessors, we know, right, have taken huge leaps in terms of performance, right? So sometime in the 70s, I think it was like 74, when we have Intel 4004, right? It was like a 4-bit processor, tiny processor, but it was a big deal then, right? Then we went to a 16-bit architecture, the famous 8086, right? That's because of which the whole, you may have heard about x86, that comes basically from this processor that Intel did at that point of time, right? So it became like a 16-bit processor. Then there was this famous Pentium processors in the 90s and early 2000s. A lot of ads in TV about it. And pretty much everybody at that time, when they used to think about computers, used to think about Intel inside, and it used to be Pentium, right? Then we went to dual core. This was the first dual core processor from Intel. And then nowadays you would have heard about Core i5, Core i6, Core i7, right? So these are all the different variations and different generations. So we're right now at the 9th generation of the Intel Core processors, right? The 9th generation is in terms of architecture. So this is what is already out today. It's called as Coffee Lake, if you've heard of it. And very soon the 10th generation will come out. It's called as Ice Lake as well. So that will be the next wave of processors, right? So if you start here, right, you've gone from about 3,500 transistors to almost 2 billion transistors now, right? There's a huge number of transistors now we have in our processors, right? So we have taken like huge leaps in terms of processor, the next generation processors, right? So, and why has this happened? It's all happened because of something called as Moore's law, right? You may have heard about this in your courses, right? So what Gordon Moore, right? Gordon Moore was one of the co-founders of Intel, and way back in 1975, so there are a couple of different variations. I'm just following on one of the variations of Moore's law, and he said that the number of transistors doubles every 2 years, right? So which means for the same area, I can pack 2x transistors, right? Which means the transistors are itself becoming smaller because of improvements in VLSI technology, the way they get manufactured, right? So that's what Moore's law was, right? And he drew a line like this, right, projecting how things would happen in the future. Now, if you look at, this is the actual curve, right? We are very, very, very close to the Moore's law, right? This is somewhere in 2015 or so, right? So we're very, very, very close to the Moore's law. So the industry has actually been able to follow what Gordon Moore had predicted way back in the 1970s, right? So that's like a huge accomplishment for the industry, right? And if you look at today, right, today's technology is like 7 nanometers, right? That's the smallest feature size, that's not the size of a transistor, but that's the smallest feature, right, in the given process today, right? So that's just 7 nanometers. Right? So 7 nanometers is a very small number, right? I mean, if you think of it, right, our hairs are something in microns, right? That's that thick they are. 7 nanometers is just too small, right? And we've almost reached that point here. So now what does it give us, right? I mean, fine, Moore's law said, yeah, I can pack more transistors, I get something. So what did we get for the end user? Because what depends is, for us, is how our microarchitectures, how our microprocessors feel like, right? So somebody just said, right, speed. This is what's happening to performance, right? So look at the leaps in performance, right? We were gaining almost 52% performance per year. So you buy a new microprocessor, you are 50% more performance than the previous one, right? And performance is your experience at the end, right? Nobody wants to open your laptop and it becomes like super slow and you're just looking at it, right? You want it to be like very, very, very fast because it's supposed to compute everything fast, right? So, and that's what we've been able to do, right? Moore's law has enabled us to do like 52% per year performance, right? Now it dropped a little bit towards the end because things became much more difficult and we were not exactly on the Moore's law trajectory as well from the previous graph, but it's still quite good, like 21% performance per year, right? And there are a lot of different processors. It's not just Intel who did this, right? There are all kinds of different processor companies, and they all benefited a lot from improvements in VLSI technology and Moore's law, right? So we continue to improve performance, and that's what, at the end, the user cares for, right? So what is performance, right? So there are two components to performance. So what does a processor do, right? You write a piece of program. The program is converted into a series of instructions, right? And the processor executes those instructions, right? That's what its performance is, right? So a processor's performance is how many instructions can it execute in a given cycle if it's operating in a clock, and what is the duration of that cycle. So if I can execute more instructions in a small time, that's performance for me, right? Because that means my task will be finished fast. Right? That's what the user cares for. I'm looking at how much time it takes for me to do a certain task, right? So it's basically two components here, right? One is instructions per cycle. The other thing is the frequency, which decides what is your cycle time. The faster the frequency, the higher the frequency, the shorter the time for the processor to do a given piece of work, more performance, right? And the number of instructions I execute in a given cycle of the clock, that's also performance. Right? So it's a product of these two things here, right? So what has happened, right? How have we got this 52%, 21% performance every generation of new processors? First, that's because of frequency. So we just saw, right, Moore's law, we're making transistors smaller, right? With advancements in VLSI technology, transistors became small, so they became very fast, right? Because transistors at the end are like a capacitor, right? And the smaller the capacitor, the smaller the capacitance, the less time it takes for you to charge it, right? So faster transistors mean automatically the amount of time you had for a given clock kept reducing, right? So your frequency kept going up, your performance kept going up, right? The other thing what computer architects did was they started making very, very deep pipelines, right? So what a pipeline does is you take a work and you split it into small portions, right? And each stage becomes a pipeline, right? So if you make a work and you split it into like smaller pipelines, you can effectively reduce the amount of work you have to do in a given clock. Right? So that helped, right? So these are the two things that made our frequency go very, very high. And the other thing what we did was we also improved on the instructions per cycle. How many instructions can I execute in a given single thread per cycle? We kept on improving it by advancements in computer architecture. Right? Computer architecture is pretty much the science of how a computer will be architected, right? How a microprocessor should look like, right? And if you keep on advancing, we kept on coming up with new techniques so that we can run more and more instructions per cycle, right? Kept removing bottlenecks from the machine, and that helped the IPC, right? So the product of IPC times frequency, which is performance, had like a huge advantage over time, right? But what's happening now, right? And that's the important thing to look at here, right? So we are right now in this area, and it's a slightly older graph, right? So we've gone beyond it. right? So what's happening out here, right? Look at the performance out here. Look at the single thread performance, right? We're almost plateauing out, right? We're not improving performance a lot, right? We're improving every generation by 5%, 10%, things of that sort, right? If you look at latest processors that come out from Intel or from AMD, right, they talk about 15% improvement in performance. Nobody talks about 50% improvement in performance anymore, right? So this is plateauing out, right? The number of transistors is still increasing. I'm able to pack more transistors, right? So Moore's law is continuing. It's slowing down, but it's still continuing, right? But this is pretty much saturating out here, right? And then one of the biggest reasons why it's saturating is because of frequency, right? So if you see here, your frequency is mostly plateauing out. I'm not able to increase the frequency further. So if you remember, right, sometime in the late 2000s, we reached around 4 gigahertz with Sandy Bridge processors, and then it's been around 4 gigahertz for a long time, right? I mean, the latest processors from Intel claim about 5 gigahertz on certain parts, but that's pretty much it, right? We've been around the same gigahertz limitation. We're not going to 6, 7, 8, 9, 10 gigahertz anymore, right? So we're not increasing frequency, right? And that's the reason why the performance is more or less in the stagnant, right? We're getting improvements. Every generation, we are making faster processors, but not as fast as we used to do earlier, right? So what caused it, right? And what happened was because of another law, right? So that's called as Dennard scaling, right? So again, in the 70s, Dennard observed, right, in IBM, I think, that what happened was with Moore's law, when the transistors became smaller, so that their power also, right? So their power density ended up remaining constant, which effectively means each transistor was consuming lesser power, right? Now, power is the amount of work you do in a given time, right? So if your power density remained constant, that allowed me to increase the frequency, right? I was getting it for free, right? Because of the improvements in VLSI technology, my frequency kept on increasing, right? Because the transistors were smaller, they were consuming lesser power, right? And therefore, my frequency kept on scaling, right? So that's what Dennard scaling was doing. But what happened somewhere around this area, right? This is somewhere in the mid 2000s. This actually law does not hold anymore, right? And we suddenly see that the power density actually started increasing, right? So the Dennard scaling was dead around 2006, right? Which means it's not going to be easy for me to keep increasing the frequency. Now, does anybody know why Dennard scaling died? I mean, have you guys studied about Dennard scaling in your courses? No? Okay. So basically what happens is, if you look at the power, right, of a transistor, there are two major components to the power, right? One is the power it consumes because of switching. So whenever you do something, a transistor has to switch, right? So when you do work, the transistor switches, it consumes power. The other thing is, because the transistor is connected to a supply voltage, it continues to leak, right? So there is always some current that keeps going from the supply to the ground, right? That's called as leakage power. Right? So there's always a leakage power component, right? Now, what happened when the transistors became very small, their oxide thickness also became very small. So the leakage power started becoming a big deal, right? Which was not that big a deal in the older processes, right? So suddenly what happens is, when I keep making a transistor smaller, my power was not scaling that well. In the past, the power also used to keep improving, right? Now the power is not improving because it's getting dominated by leakage power, right? So that's what resulted in around this time, right? And then suddenly what happened was that you didn't have an increase in frequency after that, right? You pretty much got saturated in frequency. Now, you didn't get fully saturated in frequency because people figured out newer ways to build transistors, right? They came up with high K, they came up with strained silicon, they came up with a lot of nice techniques, right? A lot of very smart people did research on it, came up with new technologies to reduce leakage, to allow frequency scaling, but it would not scale as well as it was doing in the 80s and the 90s, right? So eventually what happened was that the frequency improved a little bit or remained the same for the past several years, right? So that's what's been happening overall, right? So because of that, single thread performance became very difficult to get, right? Because one of the major components of single thread performance was frequency, right? And the frequency didn't improve much, and performance was more or less the same as before, right? So the only improvements I got was from my PC. So what happened after that was, people said, hey, okay, fine, I cannot increase the performance of one core. What if I add multi-cores, right? What if I had lots of cores, right? And then I let the user go ahead and write the program in such a way that it can go ahead and run on different cores, right? So let's say you pick a 65 core machine, right? And you somehow take your program and you split it equally among all the different cores, right? What will happen now? So it'll take 1/65th of the time to complete, right? Because each core now has to do 1/65 of the work it was doing earlier. Because I've gone ahead, I've taken the same program, I've split it and given it to all the different cores to go and execute, right? Unfortunately, there's another law, right, that comes here, right? So there are lots of laws here, right? So that's called as Amdahl's law, which says that, hey, I cannot go and split the program like this, right, into all the different cores. Most programs cannot be, right? Some programs can be, but most programs cannot be, right? So there will always be some portion which is serial, right? Which means one core will have to do some more work than all the other 64 cores, right? Which means he is going to dominate the entire performance, right? So if you look at this graph here, if just 1% of your program was not parallelizable, right? Just 99% of the program I could offload equally into all the 65 cores, but just 1% of the program had to be run on one dedicated core. You get a speed up of somewhere in the 35 to 40 range, right? Something like 40x, right? Not 65x, just because 1% of your program could not be parallelized. So I added 65 cores, but I never got a speed up of 65 times because there is some serial nature in your program, and that serial program has to be done by one core. It cannot be shared across all the 65 cores, right? So if you look out here, right, you end up at 40x speed up, right? Now, if 10% of your program is not parallelizable, your performance is just 7, 8, 9% only, right? Most of the programs we write are not designed to be multi-program, right? We write lots of if, else, this, that. Right? Even if you write a hello world program, right, it's very, very hard to go and parallelize it. Right? It's not possible to go and write a program which can be completely run on all the 65 cores, unless it's a niche application, right, which was always meant to be like a computation which can split across different cores, right? Like what GPUs, for example, do. Right? Most of the general purpose program is very, very hard to be fully parallelized. Right? So that means multi-core, yes, it gave more performance, but it's not going to give you as much performance as you would have wanted. So you can keep packing more and more and more cores, right? And yes, your performance will improve because I'm adding more cores, but then you will be limited by Amdahl's law, right? So the only way out is to increase the performance of each core, which is what single-thread performance is, right? If each core is faster, no matter what program you run, it will be faster, right? If I have just one core, it will be faster. If I have 10 cores, it will still be faster because each of those 10 cores are faster than before, right? And that's what's so important, right? I mean, you may have seen, right, so many mobile phone companies, they come up with like 8 cores, 4 cores, 10 cores, right? I mean, we go and say, oh yeah, let's go buy this particular processor because it has 8 cores in it. That doesn't tell me what the performance is, right? There can be a processor with just 2 cores in it. Each core is like super powerful as compared to the 8 small cores they have. And you may get even better performance from just 2-core machine, right? So it depends on what program you run, right? What is your use case, right? What kinds of programs are you running? Are you running very parallel programs? Are you running very sequential programs, right? And what is the single thread performance of each processor? If each processor is fast, very, very fast, no matter what program you run, it'll be faster on it, right? Right. So adding more cores helps parallel programs, but at the end of the day, what is important is what is the performance of each core, right? So that's why we need to go ahead and improve single thread performance, right? And that is what this talk is about, right? How we go and improve single thread performance, right? And what has to be done in the future, right? So if you go back, right, what we said about single thread performance, we said single thread performance is, we said single thread performance is how many instructions I execute per cycles times frequency. Now, frequency is not growing because of the end of Dennard scaling. It's hard to grow frequency. Power is not going to allow me to increase frequency, right? So what is left with me? What should I do now? Right? The only thing left for me is to increase the number of instructions I execute in a given cycle. Right? So I need to go somehow figure out how to do more instructions per cycle. And that is where computer architects come in, right? We need to figure out a microarchitecture that can go ahead and help us execute more instructions per cycle, right? If you can do that, we will continue to go back on the same performance curve that we had earlier. Okay, so there are some concepts out here, right? How can we go ahead and improve more instructions per cycle, right? So there's something called as instruction level parallelism, right? So what that means is, let's look at this small snippet of code here, right? So just 1 second. Let's look at this small snippet of code here, right? So it's saying x equals a plus b, y equals x plus c, z equals y plus d. Now, if you look at these, right? Well, excuse me for the small and the capitals, assume they're all the same. So this means this can only be executed once this is done, right? And this is also dependent on him, right? So these are all dependent instructions. These are examples of dependent instructions, right? Whatever processor you do, you first have to execute this, then execute this, then execute this, right? You cannot have instruction level parallelism out here, right? But if you look at this set of instructions, this set of instructions, and this set of instructions, they are independent of each other, right? So I can pick one instruction from here, one instruction from here, and one instruction from here, and I can execute them in parallel, right? The more, see, at the end of the day, I need to execute all the instructions. That's what my job is. I'm a microprocessor. I've been given 1,000 instructions to execute. I need to execute all of them, right? What I can do is I can take one from a chain of dependent instructions, one from another chain of dependent instructions, and one from another chain of dependent instructions, and I can execute them in parallel. Right? That gives me more instructions I can execute in a given cycle. Right? That's called as instruction level parallelism, right? Now, if you look at this loop itself, right, there are lots of independent loop iterations. I can take this and I can write this into 1,000 lines of code, right? K0 equals M0, K1 equals M1, and so on, right? And they're all independent of each other, right? So this basically gives me lots and lots of independent instruction, right? So ILP is instruction level parallelism, and this is what single thread, processors utilize it for improving single thread performance. Okay, I will go ahead and take out independent instructions from the program and I'll run them in parallel, right? Then next cycle I'll go pick as many independent instructions as I can, and I'll run them in parallel, and that's what gives me the performance that I care for, right? So now ILP is a property of an application. Some applications have a lot of ILP, right? For example, if my application was just this, it's a lot of ILP, right? All these loop iterations, I can just do an unrolling of the loop, execute all of them in parallel, and gives me a lot of performance, right? So now the thing is, you get ILP. That's the nature of your program, right? How do we exploit it? Right? So to get performance, I need to go ahead and exploit the instruction level parallelism, right? So there are two things that processors do today, right? And it's been done for like almost 20 years now, right? So one is Superscalar, the other one is out of order, right? So Superscalar simply means that if I get multiple instructions to execute, let's say I'm doing an addition, right? To do an addition, I need an adder. I need an adder circuit that can do an addition, right? Let's say I have 5 additions to be done. I'll need 5 adder circuits if I want to do them in parallel. Right? The Superscalar simply means that if I can execute n instructions in parallel, I need to have n resources to execute them in parallel. Right? So what they effectively do is they take independent instructions and they can be launched on those 5 different arithmetic units, right? And they all execute in parallel. So that's what Superscalar effectively ends up doing, right? But if your instructions are dependent, you don't have an option, right? Because the dependent instruction can only be done when the instruction on which he's dependent on is finished, right? Like the example we showed before. To get the value, to use the value of x, you first have to execute x, right? And then you can use the value of x for the next instruction, right? So dependent instructions have to be executed serially, but a lot of independent instructions can be executed in parallel, right? That's what Superscalar does. The Superscalar processors don't have one functional unit, right? They have multiple different functional units. Right? Functional units are things like arithmetic units, a divider, a multiplier, right? A shifter, whatever, right? Whatever code you write, right? You need an execution unit for that, right? So all this, it has multiple different execution units, right? And I can go ahead and execute multiple different instructions in parallel, right? That's what Superscalar does. The second concept is out of order, right? I mean, I basically need to hunt for independent instructions, right? So instead of looking at instructions as the way you've written them in your program, the processor goes and looks around and sees, hey, give me one independent instruction from here, give me one independent instruction from there, and it finds out multiple independent instructions, right, in parallel. Yeah, question? Right. So it depends, right? So what typically processors will do is they will try to break this instruction into multiple what's called as micro operations, right? Smaller instructions, right? So the part that can be done in parallel, right? That may be done in parallel, and the part that's serial will wait for the dependent instructions to finish. So you get some ILP out of it, right? So it's not at the level of instructions, but it's a level of micro instructions, right, or micro operations, which is called, right. So that's what that's a lower level detail, right, where basically we don't execute one instruction, we try to break it down into multiple micro operations and extract some parallelism from those micro operations also, right. So that's a good question. Okay, any other question here? Yeah. Mm-hmm. Right. Mm-hmm. Right. Mm-hmm. So it's an excellent point, right? So how will you write such a program, right? Typically, what you will do is you'll make the loop iteration as a parameter, right? You'll say go from I0 to I equals n, and n is going to be an input for you, right? So the processor has to figure out on runtime how many loop iterations are there, right? So I'll just get to that, right? That's called as prediction, right? So it tries to predict, right, branches, right, which is basically these kind of scenarios, right? How many loops are actually going to be there, and then try to parallelize those loops, right? So I'll just come to that, right? So it's an excellent question. Anyone else? Okay. Okay, so continuing further, right? So now we just talked about out of order and superscalar, right? Superscalar meant I had lots of execution units. Out of order meant that I will go and hunt for independent instructions by looking at the full program. Now the thing is, I can't look at the full program. There can only be a certain number of instructions that I can look in a given window of time, right? Yeah, there's a question? No. Okay, so there are two very important parameters that come for out of order modern processors, right? One is the width of the machine, and the other one is the depth of the machine, right? So what is the width? When you hear about processor width, right, you may hear that, oh, this current processor is a 4-wide processor, or is this current processor is a 2-wide processor, right? So there's a lot of specifications that are generally put out for processors, right? I mean, people will say, yeah, this is the frequency of the processor, and it is so much wide, right? Nobody typically talks about the depth, but they do talk about what is the width of the machine, right? And it has so much caches and all this stuff, right? Those are the kind of things that people talk about here, right? So processor width is effectively how much parallelism can the processor have, right? So we just talked about, right? You have multiple execution units, but you cannot put infinite number of ALU units, right? You'll put some n number of ALU units, right? That basically says I cannot execute more than n additions in parallel, right? That's what is called as the processor width. How many instructions can the processor execute in parallel? So this is the theoretical limit for IPC. When I say it's a 2-wide machine, it means it can only execute 2 instructions per cycle maximum, because it's only a 2-wide machine, which means its IPC, or instructions per cycle, cannot be more than 2, right? So that's what processor width is, right? Now again, this is in terms of instructions. The actual implementation is in terms of micro operations, so the definition is slightly different around that, right? The other concept is processor depth, right? How many instructions does the processor buffer so that it can basically figure out independent instructions? Right? The processor has to figure out the ILP in the program, right? But it cannot look at the whole program together. It's not possible, right? There'll be like too many instructions. It'll have to look and have to figure out what is independent there. So it buffers a certain number of instructions, right? And let's say it buffers 200 instructions, right? So in fact, for example, the Intel Skylake processors, which we mostly buy today, they are 4-wide and 224 instructions deep, right? So it's about 224 micro operations or 224 instructions that it looks at, and from there it tries to pick independent instructions. Okay, so that's basically what the processor depth is, right? So the larger the window, right? If you have a window, if you have a processor which is very deep, it can go look at larger portions of the program, and it can probably figure out more independent instructions, right? Because when I write a program, right, I'll have some function calls which are dependent. then I'll start doing something else, and I'll start doing something else, right, in the program, right? And those something else's can be independent portions, right? So the deeper the processor, the higher the chance that it can actually go ahead and exploit instruction level parallelism, right? So typically when processors become wider, they're also made deeper, right? Because I need to execute more instructions, which means I need to look at more instructions to figure out set of independent instructions that can be executed in parallel in a given cycle, right? So these are the two important things that happen, right? So the first thing that comes to mind, right, is if I have to increase performance, why don't I just keep making processors wider and deeper, right? I just need to have much more execution units to be added. I just need to make them much more deeper, and it should all be fine, right? Why don't I just do that, right? What's so difficult about making things wider and deeper? Unfortunately, it's not that straightforward, right? So what effectively happens is every unit in a processor can supply you certain number of instructions, right, or certain number of intermediates. So to execute an instruction, for example, you need some data, right? The data has to be read out from a structure called as a register file. Okay, you've written stuff into the register file, and the instruction needs to read those sources and then compute something and then write it back to the register file. So that's an intermediate structure that's out there. Now what happens is when you make a machine wider, you need to increase the bandwidth of these ports. I mean, the bandwidth of these structures, right? So what is bandwidth? What is bandwidth? Can somebody tell me what is bandwidth? Huh? Somebody said something. The range of frequencies. A little bit much easier definition of bandwidth. What is bandwidth? One point of time, right? Yeah, that's the right thing, right? What do you want? The 5-star? Okay, that's a good one. Yeah. So basically, it could be instructions. It could be anything. How much amount of thing you can do in a given amount of time, right? So in this case, right, if it's, let's say we're talking about the bandwidth of a register file, and let's say I'm executing X instructions, it needs to supply data for X instructions in a given cycle, right? So what effectively happens is you need to add ports to it, right? You need to add more wiring inside those register files so that you can in parallel read out much more entries from the register file, right? Unfortunately, what happens is if you just increase the bandwidth of a structure by 2 times, its area goes by 4 times, okay? Because it's like a mesh here, right? So you need to add double the number of wires to read out something. Right? You have to add more control circuitry, you have to add more data circuitry, and that's how it happens, right? So if I keep increasing the depth and the width of a machine, it becomes really, really huge, right? Right? So now what happens is if it becomes really, really huge is it's very costly because it takes a lot of die area, it's a bigger processor, right? It consumes a lot of power, right? The problem is not just this, right? There's a lot of power because as things become bigger, the wires become longer, you have to drive those long wires, you have to consume a lot of power, so things become very difficult. And then at the end, you may not be able to get your frequency also because things also become very slow. Bigger the thing is, the slower it becomes, right, to go and access it. Right? So what effectively happens is it's a very, very big challenge to simply increase the width and the depth of machine. And computer architects actually spend a lot of time coming up with very smart microarchitecture so that they can go and effectively have a wider and deeper machine without doing this kind of scaling in most places. Right? So there are a lot of smart techniques people figure out, right? How I can get an effectively wider machine and effectively deeper machine without doing a very blatant increase in number of buffers. You do have to increase it, of course, but you try not to increase exactly in the way you want to make it wider and deeper, right? And there's a lot of research, a lot of smartness that's needed out there, right? Okay. So now the second thing is, somebody asked this question, right? I don't know what is the length of the loop that I'm running, right? How many iterations the loop is going to run, right? Similar thing happens because we write a lot of code like this, right? If X is greater than 1, I'll do something, else I'm going to do something, right? So this is called as control dependent region, right? Depending on what was the value of X, I will run these number of instructions or I will run these many instructions, right? Which effectively means that these instructions become dependent on what is the outcome of this comparison, right? X greater than 1. Only when I know whether X is greater than 1 or not, I will know what portion that I have to execute, So it's a control dependent region, right? And the problem with this is I need parallel instructions, right, to improve performance. Here, because of this if and else statement, I don't know what to execute, right? And the second thing is they're not parallel because they become dependent on this one, right? So now the way to do this is, can I know in advance, right, what is the outcome of this branch? Can I know in advance how many iterations a loop is actually going to be run? Right? If I can speculate on that, right, if I can predict on that, then that's great. Then I will, if I predict that the if is the one that's going to be taken, then I can go ahead and just run the if portion of it, right? And I get more ILP, more independent instructions, because I don't need to worry about what the control is, right? So that's a very, very, very powerful idea, right? And it's one of the things that has actually helped single thread performance a lot, right? It's called as branch prediction, right? So when you have branches in a machine, right, when you have if and else statements, modern microprocessors can actually go and predict whether you want the if to execute or you want the else to execute, right? You yourself don't know. When you wrote the program, you wrote if x greater than 1, I will do this, else I will do this, right? You didn't know it because you didn't know what the data was. But the microprocessors have actually gone ahead and implemented branch predictors, and they're actually able to predict very accurately, right, whether the if will be done or the else will be done, right? So they've been like a huge plethora of predictors, right? So one of the simplest predictors is something like this, right? It says, if you look at this loop, right, the first iteration will be done, the second iteration will be done, the third iteration will be done, the fourth iteration will be done, right? Every time, the easiest predictor is to say that the next iteration will be there, because 1,000 times you are going to be running the iteration, right? So if you're on iteration number 50, predict that the 51st iteration will also happen. So instead of 1,000, let's say it was some n, parameter n, and I have no idea of the parameter n, right? The microprocessor can go ahead and predict that, yeah, the next iteration will happen. So when does it actually stop? So that's basically what the predictor has to figure out, right? So this is actually a very famous, I think it was sometime in the 1980s, it was proposed, and it's called as a 2-bit predictor. What it simply says is that I'm going to keep observing a branch, right, and see what is happening historically in it, right? Because the program is running for trillions of instructions, right? Program is running for like several seconds, right? So I'll keep observing in the past how has the branch behaved in that program, right? And if the branch has been saying that I have to be taken, right? A taken would mean that the if the else has to be done, and the not taken would mean the if has to be done, or vice versa, right? So basically, if let's say always the if of that branch is being done, right? In this case, for example, most of the times it's the loop will continue. It's only once it will say it's the end of the loop, right? So the branch will say I'm done, right, at that point of time. So if this 2-bit predictor simply figures out, puts up a small finite state machine for every branch that is of interest to it, right, and tries to learn whether it's always taken or it's always not taken, right? And they added some more sophistication on top of it, saying if, let's say, this particular branch, right, the last time this loop will say I'm not taken, right, and the branch predictor would say you're taken, because it's always saying the next iteration, next iteration. So as soon as the 1,000th iteration come, the branch predictor will go wrong, because he will say 1,001 iteration should be coming in, and he's wrong, because that's the end of the loop. That's how the program has been written. So what will happen in that case is that the whole processor will have to stall. It will have to flush everything that it has done, and it has to re-execute now, right? Because it made a wrong prediction of how the program is going to behave. So whenever you make a wrong prediction, you have to flush the whole machine, and then you're wrong, right? So the sophistication they've added here is that next time when the loop will come, right, after some point of time, again the loop will come, right, because it's part of a function, and you will call the function again, right? So when the function is called again, the loop will again execute, right? So it's smart enough. It knows that, yes, it once in a while it says I'm not going to be taken, but most of the times it says I'm going to be taken. So I will continue to predict it's taken, because I know I'm going to go wrong only once, right? In 1,000 iterations, I will go wrong exactly once, right? The last time, which is okay, right? I mean, it's a very infrequent branch misprediction, right? So that's how the branch predictor was designed, the first one. And then people went ahead and refined the predictor, right? People looked at what's called as correlating predictors, right? So if you look at these two branches, if you look at these two branches, right, it says if AA equals 2, do something. If BB equals 2, do something, right? And if AA is not equal to BB, then do something, right? Now, if you look at these two branches, right, and if you know that this branch is taken, this branch is also true, right, then you automatically know what should be the outcome of this particular branch, right? So these are correlating predictors. They say, hey, in the program, this branch is correlated with this branch and this branch. So depending on what's happened to these two branches, I can very easily predict what's going to happen to this third branch, right? So I don't need to go and do a branch computation. I only need to go just check if my prediction was correct or not. And what people have done is they've taken this concept further, right? And it's a very complex. I don't want to get into this, but this is a tag geometric history length predictor, right? This is kind of like the state-of-the-art branch predictor. It basically looks at multiple different histories of what's happening in the program, right? There are different histories that it looks at for a given branch and tries to have a good prediction, right? Now, if you look at it, right, modern branch predictors have nearly 98% plus accuracy. That's the kind of accuracy that people have developed, right? And it's not come overnight, right? There have been like lots of predictors proposed for like 20, 25 years, right? And then eventually we have reached 98% accuracy, right? See, the simplest predictor would be 50% accurate, right? You can just do probability, right? So you started with a 50% accuracy, right? And then you have eventually reached a 98% accuracy because of improvements in computer architecture. But what's happening now is even this is not enough. 98% is great, but it's still not enough, right? So this is Intel Core i7, right? And it's showing for different benchmarks what is the amount of wasteful instructions you do, right? When do you do wasteful instructions? Because if you predicted the branch wrongly, you will end up doing some other execution, right? Let's say it's an if and else. And the if was supposed to be taken, but I predicted an else. So I will go ahead and do all the work of else. And then I'll find out, hey, I was wrong. Then I will go flush myself and I'll start doing the if portion, right? I have a 98% plus accuracy for doing this prediction. But what's happening here is a lot of benchmarks, right? You are doing almost 38, 32% wasteful execution. So many useless instructions you're executing and throwing it away because the 2% is causing you so much problem, right? It's a huge problem for you, right? So even though today, and it's both power and performance, right? When I execute useless instructions, I have burnt power there and I get nothing. I'll just go back and start executing the right path again, right? So it's a huge problem, right? That 2% accuracy has to be something like 0.2% accuracy for the processors to gain the next performance, right? And it's very, very hard, right? Because people have spent 20, 25 years coming up with this tag history predictor, right? And with this tag history predictor, right? And even that 2% inaccuracy is costing a lot of performance. Yeah. So the way it happens is when you fetch an instruction, you know it's a branch, right? And at that point of time, you ask the branch filter saying, hey, is it going to be an if or is it going to be an else? The branch predictor quickly tells you, based on its prediction, that the if has to be taken. Then you go ahead and start fetching the if portion of the instruction. The way the processes work is you have written all your program, right? Your program is converted into instruction. It's somewhere in the memory. The processor keeps reading one instruction at a time and keeps executing. It's not one instruction at a time, bunch of instructions at a time and keeps executing a bunch, right? And whenever it gets a branch, it needs to know what to fetch after it, right? I mean, there's no point in fetching both because that's useless work, right? So that's where the branch predictor comes in and says, hey, you do the if. I'm predicting it's an if. Right? So the branch, the microprocessor fetches the if portion as predicted by the branch, and if it went wrong, so he will execute the branch eventually, and his branch says, hey, the prediction was wrong. You were supposed to fetch the else. Then it has to throw away whatever he has fetched so far, executed so far, start executing from the right direction. That's what causes. This is the amount of instructions you are throwing away with just 2% misprediction, right? Okay, the second big problem that we have in today's microprocessors for single-thread performance that has to be solved is memory, right? And it's classically called as the memory wall, right? We've hit the memory wall like several years, right? So what is the memory wall, right? If you look at the CPU performance, it's been growing at a pretty good, healthy rate, but the memories are not going, right? When I talk about memory, it's the RAM, right? I mean, all of you, right, when you buy a processor, you look at, right, how much RAM it has, right? What is the speed of the RAM? Is it the DDR3, whatever, 16 something hundred RAM, or is it DDR4 2133 RAM, right? So you look at the frequency of the RAM, because apart from the processor, the other important thing is how fast and what capacity of the RAM you have, right? So the RAMs or the DRAM, right, the dynamic RAM, they are not improving performance at the same rate as CPU is, right? So that basically means I can have a very fast CPU, but then I'll be limited at the memory because he's not going to supply me with data, which means I have to stall, right? So that's a huge problem, right? Because memory has very long latency and very low bandwidth. Right? It cannot supply as much data as the CPU needs, right? Because CPU is much faster, right? So that is why people went ahead and implemented what's called as caches, right? So the cache is basically based on temporal locality of data, right? So if you look at this particular piece of for loop here, your sum is 0, then you say sum equals sum plus something, and you continue the loop, right? So every time you're reading this variable from the memory, right? It's the same variable, right? There's a lot of temporal locality. Same variable is going to be accessed across many iterations. So this is the data that is very frequently being accessed, and you don't want to go to the memory all the time. So what people started doing was to put a small on-die SRAM, a static RAM, which is faster, right? But you cannot make a huge RAM because huge SRAM because it's very costly for area, right? So it's a much faster, higher bandwidth, and a lot of frequently accessed data can actually be stored in it, and you can directly access from there instead of going to the RAM, which means I'm not getting bottlenecked by the RAM. Right? So a lot depends on what is the amount of hit rate that you get in these small caches, right? If all your data resides in the small caches, you're going to be very fast because you're not limited by the memory, right? If nothing is residing in that cache, right? If let's say you have a very random way of accessing your data and nothing is residing out there, you'll go all the way to the memory and then you're done, right? You may have the fastest CPU, but you don't get any performance. Right? So this is one of the classic things that people have used to reduce the memory wall, right? And typically instead of having one big cache, right, which also becomes slow, we have always gone towards a multi-level cache hierarchy. So you'll have a small L1 cache, which is something like 32 kilobyte. Then you'll have another L2 cache, which is like 512 kilobyte. Then there will be a last level cache, which is something like 8 megabyte. These are things that are also advertised by your processor, right? So when you go buy your next processor, look at these things, right? How much cache it has? More cache, more performance. What kind of memory it has? Faster memory, more performance. What is the frequency of the processor, right? How many cores it has? How wide and deep is it? Right? All of this is decides, right? But nobody goes and tells you what branch predictor it has. Nobody will ever advertise what the branch predictor it has, right? So you need to watch out, right? If you go and buy an 8-core processor which has really bad branch predictor, don't expect it to perform as well as a single-core processor with a very good branch predictor, right? So that's why you should go and look at benchmark scores. That's probably the way to go for it. Right? Look at the reviews, right? Look at how good it does on different benchmarks and figure out what processor to pick it up. Okay? So anyways, right? So caches are basically done as multi-level, so you first look at the L1, then if you don't hit in the L1, then you look up the L2. If you don't hit in the L2, you look up the LLC. If you don't hit in the LLC, you go finally to the RAM, right? And look at the difference in cycles. If you hit here, 5 cycles. If you hit here, within 15 cycles, you get back data. If you went all the way here, it took 200 cycles for you to get that data. Right? It's a lot of latency that you have to go fight out. Okay, and lots and lots of research happens in caches, right? I mean, we just want to have much more cache hit rates, right? So people are doing a lot of works, right? People are figuring out how well to manage these caches, right? What data to be cached out there, which gives us the best performance, right? There's a lot of work on algorithms to do this stuff, right? How to design these cache hierarchies, right? How to look at the coherence for them, right? How to make sure that data is not wrongly some old stale data doesn't get supplied to you, right? Because you have multi-level caches before the memory, right? How do we do that? People are looking at cache compression, new technologies, right? Instead of using SRAM, can I use like spin torque memory or something which can give me even bigger caches than before, right? So there are lots and lots of advanced caches and lot of advanced cache techniques that are under research so that we can go and scale this whole memory wall, right? So that's where the caches stand, right? And then there is another very interesting area, right? It's called memory prefetching, right? There's a lot of work happens in memory prefetching. A lot of computer architects work on that, right? So the idea here is that even before the actual instruction comes, just like branch prediction, right? You speculate what data is it going to access much in advance, right? So what is the advantage, right? If I can predict several cycles before that I'm going to use this data, I will launch a request to the memory and get that data and keep it in the cache, right, before that instruction comes. So it effectively helps hiding the latency, right, by doing speculation. So that was controlled speculation, where you speculated which way the branch is going. This is memory speculation. You're speculating which data am I actually going to access, right? And let's get the data in advance, right? And there are lots and lots of prefetches, right? You have SPP, VLDP, BOB, stream, and all kinds of acronyms people come up with, right? So this is, if you go look at computer architecture conferences for the past like 20 years, every year you will see some new kind of prefetcher that somebody in the world will be proposing, right? Mostly coming from students, right? Students who are doing advanced research in these topics, they come up with newer and newer prefetchers, right? And every new prefetcher helps scale the memory wall, right? So, and then there are also software prefetchers, which are defined by the user itself, that need some compiler support and things of that sort, right? It's a very, very, very active and very important area of research, right? And on top of it, it just is an idea, right? A lot of research is happening on how to increase the memory, how to improve the memory itself, right? So you have things like high bandwidth memory that has come up, which is even higher bandwidth and potentially lower latency because of a new way of making memories. You have the traditional DDR4, DDR5, DDR, so on, right? Improvements in the current memory that's going on with the memory vendors. Intel has been looking at a lot of solid state drives. Beyond DRAM, there is a disk also that also creates problem for you. If you don't have enough RAM, you'll go to a disk. How can we make it faster? Right? So things like 3D cross points, SSDs, these are all meant to improve the overall memory system, right? So it's a lot of work that's happening, and a lot of advanced architecture support that's needed to support these different technologies that people are looking at. Right, and then there are other vectors as well for processor research, right? So people are looking at, okay, forget about predicting addresses and prefetching, right? What if I can predict what the data will the program generate? So even without running the program, I'll just predict that you have written a loop and you're going to generate a 0 out of it, or a 1 out of it, right? So I don't even have to execute anything. So that's very advanced stuff that people are trying to do, right? There is this whole thing about deep learning, right? So about how can we improve performance of deep learning, right? A lot of accelerators, right? A lot of special purpose accelerators that can be put alongside the core, and some of them may be visible to the software, some of them may be totally invisible, right? You don't even get to know, but the processor keeps offloading stuff to it, completes all the deep learning stuff that has to be done faster and gets back, right? So you don't have to worry about writing special kind of code here, right? And things of this sort. It's lots and lots of different technologies, right? And on top of it, you may have heard about Specter and Meltdown. Right? These are like security challenges that come because we are speculating a lot. To get more performance, we speculate on branches. So this actually exploits branch prediction, right? It knows that branches can mispredict, right? And it uses that misprediction to do whatever security vulnerability, right? So we need to speculate more because we want to get single thread performance, but we have to make sure we don't have a Specter and a Meltdown, right? So that's the kind of thing that has to be done. Yeah, question. Yes. You can, right? So what you can do is you can say that so there are constructs in software, right, where you can force a program not to speculate. So these are called as fences, for example, right? So what you say is that so the reason why Specter and Meltdown happened and similar vulnerabilities happen is because we do speculation, right? Without even finding out the branch outcome, we go ahead and do something. Now that do something was actually a rogue code, right? And the program knew you're going to speculate on the branch. He made sure that the branch filter is trained in such a bad way that you ended up doing it that particular way, right? Now, if you write a program, right, which is guarded, right, which will execute, let's say, all the instructions in order, will reduce the amount of speculation you do. Automatically, it will be very difficult for you to exploit those vulnerabilities, right? So for all the critical areas, right, all the high security portions of the program, you can add some patches and say, hey, this portion of the program, I want limited speculation. So it's going to come at the cost of performance, of course, right? If I speculate less, I'll get less performance, but I'll be more secure. And that's exactly what the challenge out here is now, right? I need to make sure that I can speculate a lot more, get a lot more performance while making sure there is no Specter meltdown happening. Right? And that needs a lot more research, right? A lot more smartness. Right? Okay, so I think I'm pretty much end of time, right? So let me conclude the talk here, right? So basically, what I try to motivate all of you here is we need to do something about single thread performance, right? There is no Dennard scaling. I mean, Moore's law is slowing down, right? We need a lot more architecture innovations, right? A lot of research is needed, right? A lot of bright minds coming up, solving all the speculation, security, memory wall, prefetching, all kinds of problems, right? Coming up with different ways of doing speculation, coming up with new technologies to make wider and deeper machines, right? All of that is basically what's going to help scale the memory wall, help avoid any security, right? Improve the amount of speculation, get performance. Single thread performance, everything in the world gains from it, right? I mean, it's not a niche thing. It helps every program, right? So that's the motivation. I'm going to end this with some very famous quotes, right? So I don't know, I'm going to let you read this stuff. These are like famous quotes of people, how they go wrong when they think that no new innovations can be done in the world, right? There won't be a market for more than five computers. I think every one of us has a computer in a phone today. Nobody would want a computer in its home, right? Can you imagine this now, right? 640 kilobytes of memory ought to be enough for him. This is a very famous quote from Bill Gates, right? We're still talking about memory wall, right? And yeah, I mean, a lot of people believe in this. I was talking with Shweta in the morning as well. Like, she also believes in this, right? Moore's law is dead. I don't believe it's dead. It's there, alive. So, and we're going to make advancements in architecture because there are going to be bright minds coming up with great research, solving the problems that are out there, getting performance. And that's what Moore's law is about. It's not about just scaling transistors. It's about the experience of the user, which is all about performance, right? We'll get more performance at lower power going forward.